Hello everyone, my name is Dylan, and today I'm going to be presenting question 5 from assignment 2. So this is the question, pause if you're interested, but I will summarize it in the next slide. So the question asks to lower the threshold voltage by 2 volts in a N-channel MOSFET. The implant dose will be of a singly charged species at 50 kiloelectron volts. The scan area is 200 centimeters squared and the implant time is 20 seconds. Now we're asked for the species that we're going to be using, the energy, which is a little bit odd because we're given the energy as well, the dose, and the beam current. Now, another interesting fact is that we have 400 angstroms of oxide already deposited, so we're going to be basically implanting through the oxide. So to decrease VT, we first have to remember this equation that we had for it, and some interesting facts to think about. First of all, that the silicon dioxide actually narrows the doping profile to be mostly at the interface, as well as the question actually mentioning that the implant actually creates a sheet of charge only at the interface. So that means we can actually discount pretty much all these terms except of the center one, or the second one, because that one actually deals with the charge at the interface. And that is what we care about. So the change of voltage, threshold voltage, is actually equivalent to the change in charge, and that means that this implant dose is going to, and because it's singly charged, it's going to be 1-to-1 to this change of charge. So we can go further and actually sub in values, -2 volts, and actually find that the implant dose will be 1.02 times 10 to the 12 per centimeter squared. This means that we need this many ions per centimeter squared as a dose of singly charged species. Now we can easily find the current by using the number that we found previously, and we can actually sub in the scanned area as well as the implant time that we desire to find that the beam current has to be 1.7 microamps, and this current is actually in amplitude because we still don't know exactly what species we're going to be using. So we can actually go into that in this slide. So let's start by remembering that acceptors will actually increase the threshold voltage as the device is in channel, right? So that means that we need a species that donates electrons. So this basically narrows down to group 5 because they all donate and they're singly charged. So we have all these atoms that we can choose from. Nitrogen, well, nitrogen is not as reactive and it has a low solubility in silicon, so we're not going to choose that one. But we can choose phosphorus, arsenic, or antimony. So knowing that, we can just take a little pause there and start thinking about implant energy, because these things go hand in hand. So the straggle and range of the species is actually quite important because they're controlled by the implant energy and the species used. And as we can remember, we want a range of 40 nanometers. So we can use this formula here at the bottom, ion concentration distribution, which is what the distribution is like in depth of this silicon substrate. Then we have the dose per area that we have to sub in, and we have straggle, which is actually the standard deviation of a Gaussian that's basically describing this distribution, and the projected range, which is the average depth at which these ions actually make it into the silicon. So we can look at the graphs here on the right, which I got from Streetman, and we can look for the 40 nanometers that I want to use to as a range. We can find the energies for each one of these species. Then from there, we can use those energies in turn to find the straggle of each one of these species. Therefore, we also have to remember that we're also assuming that silicon dioxide has similar range as silicon, because both of these tables or graphs are for silicon. So this leads us to actually find two things at once, basically get two birds with one stone. So we're going to choose phosphorus. And why is that? Well, for three reasons. So first reason, the distribution is actually good enough compared to the others, as we can see here, with the straggle is about the same. The energy needed is minimized, so we can just use 30 kiloelectron volts, which means that our power usage is going to get minimized as well. And the damage to the silicon dioxide is minimal, because the atomic mass is so small compared to the other two species. We'll be doing the least damage to the silicon dioxide. And we actually are choosing phosphorus, so this means that we're going to need 30 kiloelectron volts to get to 40 nanometers into the substrate, which is just at the interface. Now, we're actually done the question here, but I decided to do a little bit more digging around and plot these results using the equation that I used for the distribution before. And this was very interesting because we were told this is a sheet of charge, but it's actually not. When we plot this distribution, we see that the phosphorus actually is quite spread around, and it's not an actual sheet of charge as what we were told. So I'd like to thank you for listening to the presentation, and hopefully you learned something new.